Hello everyone, how are you guys? I hope everyone is fine. So I'm back and welcome. If you are seeing this again, if I am the same person you are looking again and again, then the funny part is you can't even look at me. Anyway, so we will continue from where we left in the last class. So in last couple of class we discussed couple of things about CMM and let's recap it. So in first class, we saw the overall layout in which we will be studying about CMM. Then we studied what is CMM, which was coordinate measuring machine. Then what was its principle and how it will work. So in the process of that, we studied about shapes and we studied about three different type of shapes. I will be repeating this again and again because it is very important. One was actual, then nominal, and substitute. This actual was what you got by manufacturing. Nominal was what you gave the manufacturer to manufacture. So this was given as CAD design or by drawings you gave by 2D drawings, and substitute what you got by CMM. Of course, CMM is not giving you directly the substitute shape, but it will construct. So it's better to write constructed by CMM, constructed by CMM, and this is by numerically. So this construction was done by fitting a form, fitting a form in point cloud. Now what is this? So suppose you have a component and you will try to take CMM and different points will touched by CMM and you will get a number of these points. These number of points on the job forms point cloud, and computer will take all these datas or these coordinates and finally it will fit a suitable form. Here form means suitable curve. So in last class we studied about different forms, different form fitting strategies, and these were three in number, which are most commonly used. One was least square, then another one was min-max or Chebyshev, and the third one was hybrid method. And till this point we studied. So now we will continue today from here that what will be our ultimate aim. So our ultimate aim will be to design a system that best or the closest these point clouds be obtained. If these point clouds are very exact, then of course our computer will be able to use these strategies in a proper manner, and then in by these strategies a very nice suitable form will be fit to this body, and you will be able to get a very close resemblance of the actual shape of the body. So our aim for now on will be to optimize our measurements, optimize the measurement of coordinates. So this will be our aim. But now you should ask me that, sir, if these are the coordinates, then what is the reference of it? What is the reference for these coordinates. Because till now you have studied about these coordinates in xy plane or in 3D xyz plane. So whatever you have read till now, you always had one origin. So you always had one starting point from where you started your measurements, and you did all the measurements from here. If you have to measure this point in space, then you will take projections on the x-axis, then along the y-axis, and then the z-axis. X, Y, Z, Y, anyway you can go, that's not an issue. So always you had one origin or the starting point. So now in these coordinates measurement also, you need to know what is the starting point. What is the reference for these coordinates, or what is the starting point. And today's class will be devoted to know about this. Once we are knowing it, our work will be simplified for further understanding of this machine. Okay, so let's start with the picture of CMM because that will be easier for us. So suppose this is your CMM. So this is a model of CMM. This is a bridge type of CMM, and you should not worry about it because what type of CMM are these we will be talking after this. Different structure, different types, what are the materials, that we will talk. But right now you have to understand that this is a CMM. This CMM can move front and back, means these are fixed on these rails, and this entire system can slide on these rails front and back along these directions. Similarly, this entire structure is free to slide here, left to right. So it can go left, it can go right, it can come front, it can go back. So by that you can see this probe head can cover the entire workspace of this machine. Is it fine? Now, these structures which are fixed on these rails are also connected with linear transducers. These are mounted by linear transducers. So what is the work of these linear transducers? That suppose you place an object on this, some object of any random shape. Let's put a sphere on it over here. Okay. So you put some plate or sphere of this shape in here. And now you want to measure different points on it. So what our system will do, this entire system will be fixed to another computer system wired to this machine. So you will put inputs into it, and your inputs will be for machine. That dear machine, please do me a favor. Please go backside to this distance, then right to some distance, and vertically some distance up. So you can take coordinate at this point. So you are putting some values in this, so your entire machine probe can reach this point. So these coordinates, what you are putting into the feeding into the system, are your machine coordinate system. These coordinates will determine how your machine will move from some reference point, and that reference point will be fixed. That reference point can be anywhere. It can be here or it can be here, but in general it is fixed somewhere over here, and that is given by the manufacturer. Or you can, like, manually also you can fix, but you should understand that there is some fixed point from where all these measurements will be done, and those datas can be put in this machine, and the probe end will go to this. Now for different values what you will feed in machine, this probe head will touch different points on the job, and different points will be relative to each other. So different points, so these different points on job has to be relative to each other. So you need to have some reference frame attached to job, because suppose if your machine is telling this is point A and this is point B, and the distance between these 2 points are 10 mm. So this 10 mm are the relative distance between these two. So when you say relative distance between these two, so there it's always better to fix a coordinate reference point on the job, and that will be called as part coordinate system. We will write this as PCS, part coordinate system. So let's see this again. That now take another example picture. Now you see, here is a job, this is the job, and this is a job, and this job is placed on this machine. So, and there's a system which is not shown over here, but you should know this is attached to this machine. So you can move this machine by giving inputs to this. Inputs to move machine or alter machine coordinate system. And to alt, and you can see there is a coordinate fixed into this. So this coordinate system is called part coordinate system. So your part coordinate system has some responsibilities, and those responsibilities are very simple. It establishes your orientation of job, of course, origin of measuring systems, origin of measuring systems on the job, and frame of reference in which part feature locations are defined. This was number 1, this was 2, and the third one is frame of reference in which part feature locations are defined. So to move your machine, you will get, now what you can do, one alternate method can be that you can align this job with the coordinate axis of machine. Now in above picture I can show you that in this was the machine coordinate system, that x will be in this direction, y will go back, and z will be in the direction of 2 movement. This is a pretty standard coordinate system for machine, that the if this is the front of your machine, then away from you will be the y-axis, z-axis will be in the direction of movement of tool, or here its probing device, and perpendicular to both of these will be the x-axis. This is pretty standard. It is almost for all the automated machines, CNCs. This is the standard machine coordinate system. So, but part coordinate system can be different. It depends on the orientation. So earlier time when CMM was not there, then it was a very tedious job to orient your part coordinate system parallel to your machine coordinate system. Now here you can see this is the machine coordinate system. This is the machine coordinate system. Here is y, this is z, and this is x. And your part coordinate systems are parallel. This is machine coordinate system, this is your part coordinate system, and they both are parallel to each other. So before CMM, this, like, you were forced to orient your job like this. Means part coordinate system should be parallel to machine coordinate system for accurate results. And you can pretty much understand it's not always so easy. In this you can see it's a very simple plain job, but just imagine having a sphere or some crank rod, like crank engine rod. Like, it will be very difficult to orient it. There will be so much of difficulties into it. So CMM gave you the advantage of, like, letting you be free of these orientation problems. So now the if there are two coordinate system, one machine coordinate system and another one is part coordinate system. So establishing a relation between these two became important, because there are two different coordinate system in one single use. So until unless you don't establish a relationship between them, it will be difficult. And any method by which you establish the relationship between these two is called alignment. And again, this alignment is pretty much mathematical. Why? You see, this there is one coordinate system over here, which is machine coordinate system, and there is another coordinate system which can be in any direction. This is your part coordinate system. Let this be x prime, y prime, and z prime, and let this be your x, let this be your y, and let this be z. So you can see these two coordinate system has to have some relation, and if you have studied CAD, then you must be knowing that these two are connected by, that this part coordinate system is some rotation matrix times your vector in this. So I will write vector in part coordinate system plus some translation. So this is pretty much it. Any vector in part coordinate system, sorry, any vector in machine coordinate system. Any vector in machine coordinate system will be equal to some rotation of any vector into part coordinate system plus some translation. So this is the general relationship, but this we are not supposed to do. This is taken care by machine, taken care by software. Software present in machine. Present in machine. This is present, huh? present. Now, a very common common question popping up in your brain would be why and how we do this alignment. Why is clear that we do alignment so we can get coordinates on the job with respect to itself, so we can fit some suitable form to those point clouds and get the geometry of it. So why is clear. Now another thing is, how do we do it? How this alignment is done? This is a question. So the idea of this alignment is nothing new. It is coming from the idea of two-dimensional only. Like when you give any product to be manufactured, you give them a drawing. Drawing is given for manufacturing. And these drawings are on a 2D paper, 2D paper only. Like nowadays CAD models are given, but earlier times on 2D paper, by different datum we were giving the drawing. So these drawings now also, even if on 3D, we take it by different projections, and those are just two-dimensional projections only. I will show you an example of it. Just see. Yeah. Now you can see here that this is the job, right? This is the job, and in this job has to be manufactured by machine. So the drawing will have three different projection: front view, back view, top view, and we will have some datum lines. Like suppose this line is your B, this line be your A, and into the picture our coordinate C is there. Like this is datum into the drawing, into the plane. Okay, so it is given by this cross mark. So you can see these things, and if the same for same component, if you draw the isometric drawing, so it will look something like this. See, you will have again three datum lines. Here this was B, so here it is B. This is B. Here it was A, so here this line is A, this line is A. Here into the plane was C, so C, here is the C. So you can see that if somehow you fix this plane and this plane, top plane, all the points are fixed. Okay, and all the datums are very standard things. Like this line A is the intersection of, suppose if this is plane P1, if this is plane P2, and this is your plane P3. So your is A is the Boolean of plane P1 and P2. This is Boolean of plane P2 and P3, and this is Boolean. Sorry, this B is P1 and P3. P1 and P3. This and this. This is P1. This top plane. This is P1. This is P3. So the intersection of these plane is B, and the C is intersection of plane P2 and P3. So if in software we just select these three planes, 1, 1, 2, and 3, so automatically this point will be taken as origin, and it will become the reference point for all the points measured on this component. And this point will become the origin. This point will become origin of part coordinate system. Okay. So once if you have part coordinate system and once if you have machine coordinate system, you can start doing your measurements, and then it will be very easy to have relationship between them. Like suppose I will just show you one more thing how it's become easy, that once if you have your machine coordinate system, once if you have your part coordinate system, it will become very easy. This is the origin of your, this is your origin. Let me write O dash. So this is origin of part coordinate system. This is origin of machine coordinate system. And you can see this is, suppose, like it is not necessary, but still, let us assume that this is your x dash. This axis in the downward is your y dash. And this axis be z dash. So it's now pretty much like you can understand that between this coordinate system and this coordinate system, there is a relationship, and this relationship can be very well. Suppose I am drawing this line. I'm very sorry for my drawing, but you can understand. Okay, so yeah, this is the vector, position vector of this origin. So you can establish a relationship between machine coordinate system and part coordinate system, and then you can proceed with your coordinate measuring machine. I will show you some examples how it looks in the software. I have some images like some real-time jobs which we have done a couple of times. Now see, this is how it looks in the software. It will look something of this sort. This will be your machine coordinate system reference. This is your part coordinate system reference, and this will how it will look. By selecting different planes and giving them suitable numbers, you will fix the origin. And once this origin is fixed and you are taking touching different points by the probe, such coordinates will be measured. See, see. Now here you can see, I guess, these are the coordinates. That minus 36. Now here you cannot see the reference point of part coordinate system, but it would be suppose anywhere like some corner. It's general, like we generally take any one corner for the part coordinate system. So suppose if this is your x, so of course it is not x, otherwise in this direction it would be x, or somewhere it might be here, I guess. It might be here, who knows. Here this part coordinate was not visible, but suppose if this is your x and y and z, so these coordinates are given over here. So this is how the software will show you the different values. So this is one like coordinate of one point. Similarly, you can have as many points as much possible. Then you will have one full point clouds, and once these point clouds are ready with you, then with your last class understanding of different form algorithm, you can establish the form. And so the coordinate machine will do the measurement. Okay. Now, one very common, there are a few more things which you should know. One is that this definition of part coordinate systems reference is not unique and is operator dependent. It means that suppose I am given to do the measurement. So what I can do, I can take this as the reference point, this one. And if I ask you to do the measurement, you can take this as your part coordinate system reference. And there is no difference, no problem. Like you can always take it. Either you can take this, you can take this, or suppose this corner is taken by someone. So this is not unique. It can be taken, chosen differently by different operator, and it is completely operator choice. But yes, there are few care which you have to take care, that the primary plane what we take, some care we should take care while defining part coordinate system. One is that you put tightest tolerance on the primary plane. It means that when you are starting to choose the part coordinate system, then the first plane what you will be choosing, that should have the tightest tolerance, or means the like the chances of the deviation, you should be sure that the deviation what are there, it can be there. Like suppose there is a some sort of vibration happening near the coordinate machine which is not actually desired, but suppose it is happening, then out of these three planes there may be a possibility that some plane might be vibrating and its dimension be varying with time. So you will be choosing that plane as your primary plane on which such disturbance are minimum. Like it's very like generally we take datum as the first primary plane, but still I will show you that suppose this is a prismatic job and this is the primary plane. Why? This is the datum plane, means parallel to the CMM and in contact with the working space of CMM. So this plane will have the Titan's tolerance and this will be taken as primary. And then by secondary and tertiary you can choose. Generally secondary is chosen with having maximum area. It is easy to choose actually. But these are also not very, what you say, not always feasible. Sometimes it is easier to do. If the job is what you can see before you, a job is coming of this type, then it is very easy to do. If a complicated shape and geometry is coming, then it's become difficult. But overall understanding you should have that there are two different coordinate systems. One which is related to machine movements, which is machine coordinate system. Another one is related to parts, in which the coordinates of parts are done, and that is called part coordinate system. And the relation between both of them are x of part is some rotation time matrix time x of machine, this is vector, plus the translational vector. So this you should know. This is matrix and this is vector. This is also actually a matrix, but you can write in terms of column vector, so it's not a problem. You can write this as vector, and this is also a vector. A vector in part coordinate system is equal to rotation of some machine vector plus translation. So this equation is very common, and this you will be seeing again in CAD designs, CAD modeling, and translation, rotation, scaling. I'm pretty sure you know all of them. So questions from those area can be expected because of this equation presenting the alignment. Fine. So with this, today's lecture I will close because this was the part which was remaining in last thing. So mathematically, we have seen that one, the algorithms to fit form to the point cloud and the alignment. Alignment is necessary. Alignment is the relationship between machine coordinate system and part coordinate system. So now you pretty much understand how this machine functions. So fine, with this I will close the today's class. We will again continue in next class with the structures, different types of CMM, different structures of it, what are the material by which it is constructed, and so on. then different types of accuracy we will see in subsequent classes. Thank you for today. Thank you for your time. If you feel it is helping you, kindly like, share, and subscribe. Let me know what else you would like to understand. And just for fun, if you have watched till here, can you please post time, place, and location? By the way, date also when you are watching this in the comment box. Thank you. Kaatil Kabootar signing off. Hope to see you soon in the next class. Bye.